Hi, my name is Vladimir Kornichuk and I'm a hardware engineer at Primemas. Today, I would like to run a conceptual demonstration of our upcoming SoC chiplet called Falcon and show one of its use cases. For that, I will be using two FPGA boards, one of which will play the role of our Falcon SoC, while the other one will run a simple AI accelerator capable of computing fully connected layers, or in other words, MLP models. In fact, for this demonstration, we will be running a simple MLP with two hidden layers trained on MNIST data. Now, the purpose of this demonstration is to show that the performance of the MLP engine does not significantly depend on whether it uses local memory connected to its FPGA directly or remote memory connected to it through the Falcon SoC. To show that, we'll run the model twice. During the first run, we'll only use the components available on our AI FPGA board, where the memory is directly connected to the MLP engine. The second time around, we'll use the remote memory, which is first attached to the Falcon FPGA, is only then routed to the engine. The routing is done through a chain of solid blocks, as well as a physical interface controlled by the Aurora IP. For those who might not be aware, Aurora is a serial link layer protocol that was developed by Xilinx and is now commonly used in AMD FPGAs. Of course, our real Falcon SoC will communicate through BOW IP instead, but since this IP cannot be demonstrated in packaged FPGAs, we chose the next best link available in our environment. For a fair comparison between the two memory accesses, all memory-mapped AXA interfaces in both FPGAs were configured to the same bandwidth of 6 GB per second. That ensures that the MLP engine can access both memories at the same data rate, with the only difference being the latency. Also, for convenience, both memories were memory-mapped on the AI FPGA such that each of them occupies 1/2 of the available 32-bit address space. This means that 2 GB of the space are assigned to the local memory and 2 GB are assigned to the remote memory. With this, we can seamlessly switch between the memories during the MLP engine's operation, which will be helpful for us in a bit. And finally, we'll be using the UART interface for loading the data and instructions, as well as monitoring the execution progress from the host. Okay, we are now ready to connect to our AI FPGA by using the UART. Before running the MNIST model, let's quickly check the latencies that our MLP engine has towards its local and remote memories, so that we can clearly compare the numbers. To do that, let's first set our base address to the local memory, issue a single AXA read transaction to this base address, read its latency, and repeat the process for the remote memory. As we can now see, the latency towards the local memory is 420 nanoseconds, while that towards the remote memory is 800 nanoseconds. So we have roughly a factor of 2 difference between them. Okay, now we can come back to the local memory and import the MNIST file that has been pre-trained by using the PyTorch framework. To run the MNIST, we also need to build its instruction list, which is based on the instruction set architecture used by the MLP engine, as well as the model size and the base address, which is now set to the local memory. Also, we need to load the weight, bias, as well as vector data to the DRAM used by the MLP engine, which we will do right now. Okay, we can now run the model, but before doing that, let's quickly check model's output, which returns model predictions and true labels. Of course, since we haven't run it yet, the model prediction should be somewhat random, or they are all zeros in this case. So now, let's run the model and check the model output again. Now the predictions match the labels, so we know that the model has executed correctly. Of course, this is not what we're actually curious about here. We're curious about the execution time, and we can check that by popping the log from the MLP engine. The MLP engine has a subsystem that records the timestamp for every single instruction that runs during the execution. So we can use that for in-depth analysis, or in this case, we can use that just to check the end time, which is roughly 229 or 230 microseconds. Now we can repeat the whole process for the remote memory. So we change our base address to the remote memory. We build the instruction list. We load the MNIST data. We check the model predictions, which are all zeros once again. Run the model. check the predictions again, which are now correct, so we know that the model has executed correctly, and pop the log file. As we can see, this time around, the model took 244 or 245 microseconds to run, so slightly longer than in the case of local memory. To better visualize the results, we can also plot them in Vivado waveform viewer. So here we can see three signals. First is the clock signal that we use for our MLP engine. The second one is the log file from the local memory case, and the third one is the log file from the remote memory case. As we can see, the waveforms contain all of the instructions that are ran during the execution time. If we zoom out, we will see that most of the time expectedly is spent for performing gem operations, which in our MLP engine case are also overlapped with load operations through double buffering method. If we zoom all the way out, we will see that the final instruction execution time differs between the cases slightly, but not significantly. In fact, the overhead that the remote memory adds over the local memory is just 7%. But here we have to recall that the latency difference between those two cases was almost 400 nanoseconds. In case of BOW AP that we will be using for our actual upcoming Falcon SoC chiplet, the latency difference is going to be in the range of 20 nanoseconds, so much shorter than we have in this demonstration. We can also expect that the performance difference with such short latencies is going to be much smaller and much less pronounced than we can demonstrate with the FPGAs. So that's all I have prepared for you today. So thank you for your attention and enjoy the rest of the Tech Forum.